This is section 17.8, which is about precipitation and probably more specifically how you can use the reaction quotient to predict precipitation if you know the concentration of the ions in a given solution. So, if things that we have to remember, our KSP, the solubility product constant, is a measure of solubility. It's not quite the molar solubility of the compound, but it's a measure of that solubility. So the reaction quotient, similar to other equilibrium conditions, you use the same expression that you use to calculate KSP. Things to remember: when you have KSP, which is your equilibrium constant, you are using equilibrium concentrations, but for Q, you can actually use any concentration there. Whether it's an equilibrium situation or not, it depends on the value that you obtain and how it compares to the value of KSP. So therefore, if you have several ions in solution, or you have solutions containing several ions, you can make predictions about which compound can precipitate just by looking at the value of Q. Alright? So for this particular reaction, this is KSP, right? And if you are using equilibrium concentration, then the product that you obtain there is KSP. But if you're using any concentration, then you are calculating Q. Now, what is the information that Q will give you depending on the value that you have? Well, if Q is smaller than KSP, okay, you have an unsaturated solution. And why is that? Remember, if Q is smaller, then concentrations are lower than they are supposed to be. Okay, if they are lower, then it means you can still dissolve more. That's why you have an unsaturated solution. So remember, if Q is smaller than KSP, you have an unsaturated solution. You can still dissolve more. From the point of view of precipitation, if you have an unsaturated solution, nothing is going to happen. Nothing is going to precipitate. Now, the most obvious one should be when Q is equal to KSP. You are at equilibrium conditions. Therefore, if you are an equilibrium condition, then you are saturating that solution because you have already reached the molar solubility for that particular substance. So here, for solubility equilibria, if you are already at equilibrium, then it means you have a saturated solution. Okay? Now, in the case that Q is larger than your constant, all right, so this means that concentrations are higher than they are supposed to be. Okay, and if they are higher than they are supposed to be, what does that mean? Well, you have concentrations that are higher than the molar solubility. The molar solubility is the maximum amount that you can dissolve in water. Q larger than KSP means you are past the molar solubility. You have dissolved probably more than required. That will give you a super saturated solution. I mean, if everything is dissolved, then you have a super saturated solution, and what that really means is that precipitation will happen. Okay, remember, if it's a supersaturated solution, any disturbance will cause the precipitation of the solid, but the precipitation will occur because those concentrations of those ions are higher than they are supposed to be according to the solubility equilibrium. Okay, so how can you use that in a practical approach? So you have two solutions here. One contains silver perchlorate and the other contains sodium chloride. Okay, so if you are mixing these two, normally what you would do in 105 is that you have this reaction plus NaCl in aqueous solution, and what you are going to get out of this is a precipitate. Okay, the sodium perchlorate remains in solution, but the silver chloride precipitates, or that's the story that we knew from 105. Well, not so much. We have to check now because we know about solubility equilibria, we have to check whether silver chloride will actually precipitate out of these solutions, because it will depend on how these concentrations compare to the solubility product. So for silver chloride, KSP is equal to 177 10 to the negative 10. Okay, so we need to compare these concentrations to that KSP, but not so fast, because remember that here you are mixing equal volumes. Okay, what does that mean? You are mixing two solutions for which the concentration of the individual solutions is 0.0015. Okay, so what is the final volume? If you are mixing equal volumes, then the final volume is double the volume. Okay, let's say you don't really need the correct number, but if you have 100 milliliters plus 100 milliliters, those are equal volumes, you end up with a final volume that is equal to 200 milliliters, right? So if you are doubling the volume, then your concentration, for example, the concentration of silver perchlorate is going to be, the final concentration is going to be 1/2 of the initial concentration. Okay, so the final concentration is going to be 1/2 of 0.0015. All right. So then that goes also for for sodium chloride, because you actually have the same concentration in those individual solutions. So therefore, if this is our concentration, then Q, and we are saying Q because we don't really know if those concentrations are equilibrium concentrations, so we have to use Q. So is 1/2 0.0015 times 1/2 0.0015. Okay, remember, silver chloride is a 1:2 salt, and what we get here is 563 10 to the negative 7. So if we compare that to 177 10 to the negative 10, then it turns out that this is larger. So Q is larger than K, and therefore silver chloride will precipitate. All right, we can use this to our advantage, because now we can selective precipitate ions in solution. What does that mean? So if you have different ions, the cations or anions or whatever it is that you want to precipitate, I mean, you can use a common reagent, a common reactant that will precipitate those ions. Okay, and selective precipitation means that you are going to precipitate one of those ions while the other remains in solution. Okay, so you can go the way in which you want to precipitate everything, or you just want to precipitate one of the components of that solution. So for example, if you have a solution that contains silver and magnesium, and we know that, for example, chloride, if you add chloride, it will precipitate your silver from the solution. Well, we know that silver chloride is insoluble. All right, compared to magnesium chloride, which is soluble. So by adding, for example, again here, if you add sodium chloride, you will precipitate silver chloride while the magnesium chloride remains in solution. So that's the purpose of the selective precipitation, being able to separate ions based on different solubilities. Okay, so that the requirement here is that they have to be the solubility of these compounds have to be significantly different. So in this case now we have barium and magnesium ions, and we have two options here. We can try to use carbonate to precipitate those ions, or we can use phosphate to precipitate those ions. What do we need to do here? Well, we need to compare the values of KSP for these ions. These are divalent ions, so if you're using carbonate, then you will be producing barium carbonate and magnesium carbonate. If you are using phosphate, then you are obtaining barium 3PO4 as barium phosphate and magnesium phosphate. Okay, the good thing about these salts is that they have the same stoichiometry. These are 1 to 2 salts and these are 1 to 5 salts. So if you take a look at the value of KSP, it should be enough to tell you the difference in solubilities. So in particular, for barium carbonate, the KSP is equal to 2.58 10 to the negative 9, and the KSP for magnesium carbonate is 6.82 10 to the negative 6. So there is a nice difference here, about 3 orders of magnitude, barium carbonate being more insoluble, so to speak. Okay? But let's compare what happens with the phosphate. So for barium phosphate, the KSP is equal to 340 10 to the negative 23. And for magnesium phosphate, it is 104 10 to the negative 24. So you have, what color to use here? Here you have 3 orders, and here you only have 1 order of magnitude difference. Okay, 3 orders difference, 1 order difference. So which one you would pick between, remember the question is between sodium carbonate and sodium phosphate, which of these salts you are going to use to selectively precipitate barium out of that solution. So because you have a larger difference in solubility between barium carbonate and magnesium carbonate, then you would pick sodium carbonate to precipitate barium in presence of magnesium. Okay, why you don't use sodium phosphate? These are too close in solubility. All right, so that's why you would pick sodium carbonate. Now, a more interesting case is if you have the concentrations of those ions and then you want to determine how much you need to start precipitating these compounds, then you will have a problem like this. So in this case, you have iron and magnesium, and you're using carbonate to precipitate them. All right. So if you are using carbonate, then what the equilibriums that you are looking at here, so that you practice your reactions, is iron carbonate, because it's iron 2, that goes to iron 2 plus carbonate. Okay, and for this you have KSP equal to 3.2 10 to the negative 11. And for magnesium carbonate, we have magnesium 2 plus carbonate, and the KSP here is equal to 3.5 10 to the negative 8. All right, so the first question here, which cation precipitates first? Since they have the same stoichiometry, then the one that will precipitate first, based on the value of KSP, because they have the same stoichiometry, you can compare the KSPs directly. So the one that precipitates first is the one with the smallest KSP, and that would be, iron carbonate. Or more specifically, iron is the cation that is going to precipitate first. Why? Because KSP is smaller. Now, the next part of the question, what minimum concentration of carbonate do you need? Well, if KSP is equal to the concentration of iron 2 plus times the concentration of carbonate, right? And you already know that the concentration of iron is 0.022 molar. Well, you have the concentration of iron, you have KSP. Well, let's find out what concentration of carbonate will trigger that precipitation. So concentration of carbonate is going to be equal to your KSP divided by the concentration of iron 2. Alright? So concentration of carbonate is equal to KSP 3.2 10 to the negative 11 divided by your concentration of iron 0.022, and this is equal to 149 10 to the negative 9. So this is the concentration of potassium carbonate needed to start precipitating iron. Okay, at that point, when the concentration of carbonate reaches that point, then you will start seeing a precipitate of iron carbonate. Okay, so that's the first question. The second question here, this is a little trickier. Now, what is the remaining concentration of the cation that precipitates first? We already know who that is, right? The cation that precipitates first. That's iron 2 plus. So we want to know what is the concentration of iron 2 plus. When the second starts precipitating, what is the second? The second is magnesium. Now, when does magnesium precipitate? So we have our KSP here, right? So in order for magnesium to precipitate, then what is the concentration of carbonate that you need? So KSP is concentration of magnesium times concentration of carbonate. This now is 0.014. Therefore, your concentration of carbonate is going to be KSP divided by magnesium, right? So concentration of carbonate is equal to 3.5 10 to the negative 8 divided by 0.014 molar. All right, and this is equal to 2.5 10 to the negative 6 molar. So you went from 10 to the negative 9, you started precipitating iron, and when the concentration of carbonate reaches 2.5 10 to the negative 6, then magnesium starts precipitating. But then how do you determine what is the concentration of iron when you reach that point? Well, you have to assume that now this is concentration of carbonate, and now we are going to determine what is the concentration of iron when the carbonate reaches that point. So let's change color here. So KSP equal iron times carbonate. In the previous step, in the previous slide, we were calculating carbonate. Now we are going to calculate iron with this concentration of carbonate. So the concentration of iron is going to be KSP for iron carbonate. Very important that step. Iron carbonate. Alright, so 3.2 10 to the negative 11 divided by the concentration of carbonate, which is now 2.5 10 to the negative 6. Okay, and this is equal to 128 10 to the negative 5. Okay, so you started with the initial concentration of iron, right, equal to 0.022 molar, and you went all the way to 128 10 to the negative 5. Okay, so how much does that represent from your original concentration? Well, the ratio, your final iron divided by your initial iron, is equal to 128 10 to the negative 5 divided by 0.022. And let's say let's say we see it from the point of view of a percentage. Okay, 128 10 to the negative 5 divided by 0.022 times 100, this is equal to 0.058%. So when magnesium starts precipitating, the amount of iron that remains in solution is just 0.058% of the original amount that you had at the beginning. In other words, if we take 100 minus 0.058, okay, this is equal to 99.942%. What does that number mean? 99.942% of iron was removed before magnesium started precipitating. Okay, and that is the value of selective precipitation, in which you are able to kind of completely remove most of that ion before the other one starts precipitating. Okay, so that's the usefulness of this sort of technique. All right.